Hello, my name is João Vaz Carneiro, and I'm a graduate research assistant at the University of Colorado Boulder. I'd like to just acknowledge my co-authors, Cody Allard from LASP, and my advisor, Dr. Hans-Peter Schaub. And today I'm going to be talking about rotating rigid body dynamics architecture for spacecraft simulation software implementation. That's a bit of a mouthful, but I'd like to start off with just a thought experiment. So let's say that you have a complex spacecraft that you want to simulate, right? How do you go about that? What do you start with? Well, you might start with a rigid hub. That's where the components, the instruments, whatever sensors you need to, that's where they're attached to, right? Then you're probably going to need power. So we add power generating devices. Those could be flexible solar arrays or those deployable hinged panels. You need to control the spacecraft as well. So let's add some management control devices. Usually they're reaction wheels, but they can also be CMGs or ACS thrusters. And finally, you might add communication devices so you can talk to the spacecraft. These can be fixed or they can also be gimbaled. And so really the question that we're answering is, how are these components simulated? And I'm going to start off with an example of a hinged solar panel. So here we have a rigid hub in gray, and we have attached two solar panels in blue, right? These solar panels are hinged, so they rotate about that single axis. And the way we implement this in software, we might start off with, okay, well, we know that the solar panels are hinged, so let's define a frame for that solar panel. And let's define one of the unit vectors to be along that hinge, right? So that's the first decision. And then you also know that the center of mass of the solar panel is, somewhere in the middle of the panel. So let's say that the second axis is along that center of mass offset, right? You can then just choose the third axis so that it becomes a right-hand frame. But that's how you typically go about defining this hinged solar panel, right? This rigid body that rotates about a single axis. So that's an approach. What about a reaction wheel, a control device? Well, we know that the reaction wheel is basically a disk that rotates about a spin axis. So we can choose one of the unit vectors to be along that spin axis. And then, it can have a center of mass offset or not. Most of the time it's balanced. So we just assume that the center of mass is located in the center of the disk. So you can just choose the other two unit vectors as you wish. The point that I'm trying to get at here is that for the solar panels and for the reaction wheels, we chose two different approaches, right? We're still defining frames, we're defining center of mass offsets, we'll probably need to define an inertia and the mass, but we're taking different approaches. We're saying that the unit vectors are this or that because it makes sense for that specific component. However, from a dynamics standpoint, these two components represent the same physical reality. They are both rigid bodies rotating about a single axis. They have a center of mass, they have inertia, but from a dynamic standpoint, again, they're the same. However, we define them differently because we make these assumptions that the reaction wheel is balanced, or that one of the axes is along that hinge vector. And the question that we're really trying to answer here is, can we generalize this? Can we propose a framework where we define the equations of motion and we define these components in a more general way, such that we don't have to define these two different components two different ways, because at their core, these components represent the same physical reality? And the answer to this question is yes, otherwise I wouldn't be talking to you now. And so we start off by proposing a generalized dynamics architecture. So for example, for the 1 degree of freedom class, so this would be a component that is rotating about a single axis. We have some common properties. We need a mass, we need inertia, we need the center of mass location, we need a spin axis, and we need some sort of frame conversion between the component frame and the body frame, right? So these are shared properties. We also know that these components have the same general equations of motion. The mass property contributions for the system center of mass and the system's inertia are also identical. And we also need to account for energy and momentum contributions. This is mainly for validation purposes, but these are also shared among this class. So once we have that class, what we can do is we can inherit this class and create specific components. So for example, a solar panel is a 1 degree of freedom rotating rigid body, but besides these properties I've already mentioned, you also need to define a normal vector to know how well the power is being generated. You also need a surface area to know how much power you're producing. Reaction wheel, you would maybe assign a maximum torque or a maximum wheel speed. So you really inherit from this shared class, and then each module adds its own particular methods or particular variables. We can actually do the exact same thing for a 2 degree of freedom system. So this would represent, instead of a one body rotating about a single axis, we have 2 bodies rotating about their own axis, right? Again, we have masses, inertias, all of that. We also have shared equations of motion for these type of components, mass property contributions, and the energy momentum contributions as well. And again, we have this shared class that we can then inherit from, and we can create solar panels. We can have a dual hinged solar panel. We can have CMGs, these control moment gyroscopes, which are just sort of, they have a frame and then a disc that rotates about that frame, or even the 2-axis high gain gimbal antenna, right? Again, these particular components have a lot of shared properties, but you have to define some additional variables and methods. And this is really powerful from a software implementation perspective, because, well, you only have to derive the equations of motion once in a generalized way, but also all the validation work only has to be done once, only has to be done for the shared equations of motion and all the shared functions. And that saves a lot of time for the developer and for just the amount, saves on the amount of unit tests that a software may have, right? So with the architecture out of the way, I would just like to talk a little bit about how we actually go about deriving the equations of motion for these components. I will start with the simplest case, the single axis rotating rigid body. And the problem statement is rather simple. We have a hub in gray. The hub has its own center of mass, BC, has its own frame, B, and attached to that hub in blue is a spinning body. That spinning body also has its own frame, S, has its own center of mass location, SC, and it has an axis about which it rotates, S hat, and the angle about that axis, S hat, is called theta, and the angle rate is theta dot. So when we do this problem setup, these properties are general. In the derivations, we make absolutely no assumptions on what the frame is, what the spin axis might be. The spin axis doesn't have to be aligned with one of the unit vectors. Where the center of mass location is, it's a general center of mass location. What the inertia might look like. And so from just a derivation standpoint, it is all abstracted out. It's all general. There are quite a few details about this spin axis. We can actually apply torques to the spin axis, control torques to make sure that we're settling at the desired theta. We can also add some spring and dampers, and we can lock the axis at a particular angle. This isn't really important for the 1 degree of freedom case, but for the 2 degree of freedom case, it is rather important. So the system, the spacecraft, now has 7 degrees of freedom. We have 3 degrees of freedom for the translation. That would be position and velocity. 3 degrees of freedom for the rotation. That would be attitude and angular velocity of the system. And then we have an additional degree of freedom that is the angle about S hat, right? So how do we actually go from here? How do we actually go about deriving the equations of motion? So we start off with the translation equations of motion, and for this one, we include the hub and the spinning body, so we include the entire system. Obviously, as the spinning body rotates, and especially if there's a center of mass offset, this will change the center of mass of the system, and also have an impact on the center of mass time derivative. Obviously, because we're focusing on the translation side of things, the system is driven by external forces. So here are some of the equations that we use. I won't go into too much detail, but I just wanted to point out that we always start from fundamental principles. So here we're just starting with F equals ma, Newton's second law. And then after applying all the contributions from the hub and the spinning body and writing that in a compact form, we actually arrive at the translation equations of motion. So that's 3 degrees of freedom out, the position and velocity. Now on to the rotational equations of motion. We again consider the entire system. As the spinning body rotates, it will have an impact on the inertia matrix and on the inertia matrix time derivative. And here the system is driven by external torques. Again, these are some of the equations that we use. I just want to point out that we, again, start from fundamental principles. This is Euler's equation, H dot equals L. The torque is equal to the time derivative of the angular momentum. And once we substitute all the contributions and write it again in a compact form, we arrive at this final equation for the rotational equations of motion. So that's 3 for position and velocity, 3 degrees of freedom for the for attitude and angular velocity. And now we need that additional degree of freedom. And one thing that I wanted to point out first is how we leverage this very important equation, the matrix transport theorem. Now, this matrix transport theorem is completely analogous to the vector transport theorem. And what it says is it relates the time derivative of an inertia as seen by frame A with the time derivative of the inertia as seen by frame B, right? So obviously the time derivative of the inertia I with respect to frame A is equal to the time derivative of the inertia with respect to frame B plus these 2 terms. And so that is how, by leveraging this, that's why we don't need to specify frames. That's why we don't need to specify unit vectors. Because without this result, we would have to, at some point, define a frame, define the unit vectors with respect to the B frame, and then go from there. And that's what's been done. But that is not a general approach because we have to fix a frame at some point. We have to make that decision. And with that, we can actually derive the spinner's rotational equations of motion. Now here, we only consider the spinning body. We don't consider the hub. However, the spinning body is still attached to the hub. So the inertial states of the spinning body are impacted by the hub because it is connected through it. And in this case, the system is actually driven by internal torques between the hub and the spinning body. And we arrive at these equations. Again, H dot equals to L, pretty standard, and we get to this final equations of motion. So this is all good. This all looks good, right? But you might be asking, how do you actually know if these equations of motion are correct, right? And so we actually go through a quite extensive process of validating these equations of motion. And the way we do that is we know that the components that we're simulating represent physical components. They represent reality, right? And because they represent reality, they have to abide by physical laws. And the ones we use are these physical conservation laws. There are some properties that have to remain constant, right? In our case, when we set up the spacecraft in an environment where only conservative forces and torques are present, we know that angular momentum and energy of the system have to be conserved. In fact, the orbital angular momentum, the orbital energy, as well as the rotational angular momentum and the rotational energy of the system have to be preserved. And that's exactly what we see. So these are the 2 plots for the orbital properties. On the left, orbital angular momentum, on the right, orbital energy, and we see that they are actually conserved, right? They don't look particularly constant, but the y-axis is on the order of 10 to the minus 14, and this random walk is actually quite typical of fixed time step integrators like the one we use. We actually use RK4, right? For the rotational side of things, we see very similar results. There's still this random walk, but the quantities are being conserved. This is just issues with numerical propagation and just numerical noise, right? So that's great. We validated that the equations of motion are correct and that they actually represent these rotating rigid bodies. Now, onto the dual axis rotating rigid bodies. I'm not going to go through all the math. I'm just going to go through the problem statement because the approach is rather similar. And if you're really interested in the math behind it, I just suggest that you look at the paper. But here again, in gray, we have the hub. And now we have attached to it a lower spinning body, which has its own S1 frame, S1 hat spin axis, and SC1 center of mass, and an upper spinning body with an S2 frame, S2 hat spin axis, and SC2 center of mass location, right? So the problem center is rather similar. Obviously, we have two bodies now because it is a 2-degree of freedom system. But again, in the derivation, we do not make any assumptions on what the frames might look like, if the spin axes are aligned with the unit vectors or not, if the inertia is diagonal or not. We make absolutely no assumptions on any of that. As before, we can actually apply torques to each of the axes, control torque or spring and damper, and we can also lock each axis individually. Now, this is important because when you're controlling this 2-axis system, it is sometimes very useful to lock one of the axes as you control the other body, then lock the body that you've already controlled and control the other body. That way you don't have to account for the gyroscopics, and you don't have to account for this cross-coupling that happens when both axes are free to rotate. Now, this with the two bodies represents a chain of rotary joints, of 1D joints, but what we actually found out through the derivation is that you can set the mass and inertia of the lower spinning body to 0, and what that essentially does is it creates a universal joint. So you only have one body rotating about 2 possible axes. And here we have 8 degrees of freedom. We have 3 for position and velocity, 3 for rotation, and the 2 angles, right? And I'm not going to bore you with the math, but after a lot of math, we can actually conclude that this is actually working through the exact same approach for the equations of motion, and we validate it the same way. We know that the angular momentum and energy properties must be conserved, and that's exactly what we see here. Both orbital and rotational angular momentum and orbital and rotational energy are conserved. We still see this walk, but yeah, this just means that our software implementation and our derivation is working exactly as intended. And with that, I will just conclude by saying that we've proposed the general dynamics architecture that minimizes code repetition, but also centralizes a lot of the validation for the equations of motion and for those shared methods for the 1DOF and 2DOF classes. When we derive the equations of motion, we actually make absolutely no assumptions on the frame, on the spin axis, the center of mass location, the mass, or the inertia matrix of the bodies. And we obviously validate the results by making sure that energy and angular momentum conservation are true for the entire simulation. And with that, thank you for watching.